Welcome to the lecture on paired samples hypothesis testing. This is a lecture that's going to guide you through how to complete the paired samples hypothesis test for the final project portion. The data that we're looking at right here allows us to explore the salaries in Atlanta compared to Houston, paired on the individual occupations that are in both Atlanta and Houston. So, for example, in Atlanta, the salary for an attorney would be $107,000, or 107 $1,457. In Houston, it's going to be $123,589. And for each one of these occupations, each city has their own salary. And so you're going to also so the dependent variable is going to be salaries, and the independent variable is going to be Atlanta and Houston. So salaries are dependent on the city that they're in, and they happen to be paired on each one of these individual occupations. Because they are paired on each one of these individual occupations, what we have the ability to do is take a difference score. And what a difference score is when you take the value of the sample of the second sample and subtract it from the first sample. And so what I just did there, and I'll show you, I took C5 minus D5, which gives me a difference of 16,132. So what that means is that the salaries for Houston attorneys on average are $16,132 more than the salaries for attorneys in Atlanta. And so all that we've got to do now is take the difference score, take that formula where we took C5 minus D5, and you see this fun little box in the bottom right-hand corner. You hover over it until your cursor changes, and just double-click. And copy that same formula all the way down until the very end. So every single occupation now has a value for Atlanta, now has a value for Houston, and now has a difference score. And the truth is the only thing that we are looking at now is the difference score. We are no longer looking at Atlanta and Houston. We are only looking at the difference score. And so we are going to run descriptive statistics on all three of them, because a little bit later we're going to be able to say, hey, this is the mean of Atlanta, this is the mean of Houston, these are the descriptives of these two different populations. But for the actual test, the only thing that is actually being looked at is the mean of the difference score. So we're going to run descriptive statistics. So I'm going to do data analysis. I'm going to click on descriptive statistics, press OK, and I'm going to select all three of them, Atlanta, Houston, and the difference score. Now, I'm not running the actual test right now. I'm just running the descriptive statistics, and then for the output range, I'm going to put it right here. And I want the summary statistics, I want the confidence level for the mean. I want to have, let's say, a 95% confidence level with a 5% chance of type 1 error. I want the max and the min value for all three of them. So now I have Atlanta, Houston, and the difference score. And so I am going to, let's do this. We're going to make it a little bit easier to see. And I'm going to color code these. So we've got Atlanta is going to be gray. And then we've got Houston is going to be green, just so you can keep up with what's going on over on the left-hand side. And then the difference score is going to be that salmon color. These colors correspond with their corresponding column. And so now we're going to come over here and we're going to do some, we're going to write in all of the information about our test. Okay, so first of all, do we know whether or not it's going to be an upper tail or lower tail test? We have no clue. I don't know if Atlanta has a higher salary or if Houston has higher salaries. I just don't know. So I'm going to put a two-tail test. Okay, next I want to know, should I run a z, a t, or chi-squared for my test statistic? In order to do that, I have to know what is the degrees of freedom. The degrees of freedom, unlike independent samples, the degrees of freedom only looks at the difference score. Independent samples looks at both of these together, but we're only looking at the difference score. So because of that, we are only looking at 84 values. So because we're only looking at 84 values, the degrees of freedom is going to be 83, making it so that we should be using a t-score. So we're going to be using a t-distribution, and then for our declared alpha, like I said earlier, we have a 0.05 declared alpha. Then we have the sample 1 mean, standard deviation, and size. So let's come over here. Sample 1 mean, standard deviation, and size. Control C. So I copied that, and I'm going to paste it. And I'm going to paste just the values. And then I need the sample 2 mean and the sample 2 standard deviation. Mean, standard deviation, Control C. Whoops. And I want just the values again. And then what's the mean of the difference score? And the standard deviation of the difference score, Control C. Paste just the values. And then what's the margin of error? And the margin of error is going to be, if you just come all the way down here, you'll see this is the margin of error. That is, we are 95% confident that this is the actual difference score, okay? That this is the actual average difference score plus or minus 887 0.5, okay? Values. And so we've got the margin of error, we've got the standard deviation, and notice I only have one sample size. Why do I only have one sample size? I don't have the sample 2 size, and I don't have the mean of the difference score. I don't have the difference score size. The reason being is because all of them are the same. So because all of them are the same, we just assume that this is also going to be 84, and this is also going to be 84. And if it's not 84, then you did something wrong. But every single one of them has to be the same, okay? So next, we need to formulate our research question. We have the salaries of both Atlanta and Houston. So our research question is the average difference between the average salary of the employees in Atlanta compared to Houston by occupation different than 0? And I know that there are two averages in there, and the reason why is because each of our individual observations in Atlanta and Houston are also averages of the occupations. So this is the average salary of the occupation of civil engineer from Atlanta. This is the average salary for the occupation of civil engineer from Houston. Are the differences between Atlanta and Houston different than 0? If it's equal to 0, then there's no difference. But if it's different, if it's greater than or less than 0, then there is a significant, or then there is a difference. Okay, and so that's our research question. Is there a difference in the averages of the paired samples? So that brings us to the purpose. If you want to know the purposes of running paired samples, come down here to where it says paired reference, and you're going to see, okay, we've got the paired purposes. Determine if there's changes over time between two related groups. Okay, so is there, you would have one time earlier, one time later, and see if there's a change over time. Determine if there's differences between conditions. So you've got one, in that's in the desert, one that's in the Arctic. Are they different in the way that they perform? Difference between measurements. You've got the ACT versus the SAT. Is there really a difference in the way that it's measuring students? And then determine if there's a difference between matched pairs. And that's what we're doing right here. We've got matched pairs, the matched pairs of Atlanta and Houston, and they are matched on the occupation. Okay, so we've got the purpose is determine if there's a difference in salaries in Atlanta compared to Houston by job type. So that's the purpose of running the test. Next, we've got the anticipated outcome. which is that we believe that there will be a difference, but it's not known what the difference is going to be. Okay. Next, assumption 1. So we're going to go through and we're going to test the assumptions. The one dependent variable. Okay, so what is the one dependent variable, and is it measured at the continuous level? The dependent variable is salaries. We already mentioned that, salaries, and salaries are continuous. Next, what is the one independent categorical variable consisting of two categories dependent on each other? So the independent categorical variable is location, and they are paired on job type. So you've got two different locations, but what everything is paired on is the job type or the occupation. So I think I put occupation up there. So I'm going to put occupation right there. And then next we're going to run a box and whisker plot for the difference scores. So I'm going to come over here to the difference scores and I'm going to highlight it. I'm going to highlight all of the difference scores and I'm going to say insert. And I'm going to go to this chart right here and click on box and whisker. And you notice I've got this wonderful box and whisker, and I'm going to cut it and bring it over here. And I'm going to paste it right there. Okay, so I've got this box and whisker plot, and I am titling it Difference Scores Between Atlanta and Houston. Notice Atlanta comes first, Houston comes second, in that order, and we need to make sure that everything that we write goes in that order. Do we think that Atlanta is going to be greater than Houston, less than Houston? You know, everything needs to be phrased from Atlanta comes before Houston. So I'm going to put this right over here, and we're going to put all of these values in right here. So I'm going to double click on this and click add chart elements, data labels, left, and it gives us all of these data labels right here. All of these data labels right there. And so now we can actually put in all the different information. So this is for the difference scores. And that's all that you need to do for this particular that's all that you have to do for this particular test is the difference scores. You don't have to do the charts for the other two variables. Okay, so first of all, the max value that is not an outlier is going to be 6,280. Okay, so 6,280. Then what is Q3? That's going to be 821.5. Then what is the median? That's going to be negative 710.5. And negative is correct because we're talking about difference scores. So the median is a negative. And then Q1, what is the value of Q1? Which is negative 2,879.25. And then what is the minimum value that's not an outlier? It's going to be negative 8,330. And then the mean, which if you double click on that, we can make that fill color white. There we go. Now we can see the mean. The mean is going to be, let's see here, negative 934.61. And then the number of outliers above, there are 2 outliers above. And then the number of outliers below, there's 3 outliers below. And what you're going to want to do is actually put in a little bit more information about these outliers if there's only this few. And so right over here, I actually already put in the information. So the outliers above, in other words, where Houston has a higher salary than Atlanta, we have 2 salaries, which is the solution architect and the user interface designer, which those are significant outliers where Houston is a lot higher than Atlanta. And then we have 3 outliers below where Atlanta is a lot higher than Houston. And the way that I found these is I came over here and I said, okay, I want to sort these. And I want to sort smallest to largest. And you notice these are the 3 outliers below. And so I copied these, brought them over there. Then I sorted largest to smallest. And then I said, okay, these are the 2 outliers that are above. And so it was really easy. I just put a filter on there. And the way that you put a filter on there, you highlight everything. And you say home, sort filter. and you click on filter, and it allows you to filter all of these pretty much however you want to filter them. Okay, so now that I have that information, we can keep moving on. We've got the box and whisker, and there are outliers. However, because these outliers are actually pretty evenly dispersed above and below, my thoughts are that we're going to be dealing with data that might be a little flat. But it's really not going to be skewed. It's not going to affect it too much because there's a few outliers above and a few outliers below. It's really not that big of a deal. And so I'm going to come in here and I'm going to say, okay, are there any significant outliers in the differences between the two groups? Yes, there are 5 outliers. 2 are above, 2 are, here we go, 2 are above and 3 are below. Or, let's see, 2 are above and 3 are below. So as 2 are above and 3 are below, the outliers do not skew the data. Okay. Next is the distribution of the differences between dependent variables. Is it normally distributed? There's a couple things that we need to look at. We need to look at the skewness and kurtosis, which we'll do that first. We'll come right over here and we will look at the skewness and kurtosis. And so the kurtosis, remember how I said that it might actually be flat? So it's not. It's actually very much so leptokurtic. That means that it's really highly concentrated in the center, which is funny because it's really highly concentrated in the center, but there are certain ones that are really far out there as well. And so what we're seeing is that overall, the difference scores are very close to similar to each other. But there are some that are, outside. So it's got a high kurtosis, which means that it's leptokurtic, but it's still within 3 standard deviations of being perfectly normal. So because of that, I'm actually not concerned about it. Kurtosis isn't something that we have to worry about quite as much, but skewness is something that we've got to worry about a little bit more. But because this skewness is less than 1 standard deviation away from being perfectly normal, we're not worried about it either. So we're going to make the histogram, which there's, I'm going to show you a really cool way to make a histogram. Are you ready? So I'm going to copy this, Control C, and you're like, oh, it just made another box and whisker. You're right, it did. But what we're going to do here is we're going to go to Insert, we're going to click on this chart, and we're going to say, okay, I want you to change it to a histogram. So what did it do? It just changed it to a histogram. So as long as you click on the chart beforehand and you just click right here and you say, hey, just change it to a histogram, takes the exact same data and just changes it to a histogram. However, this is not a histogram, is it? It is not, and the reason why it's not is because there's gap widths. So we're going to get rid of those gap widths. And so now I got rid of those. And you can see the distribution looks really normal. This looks like a really good distribution, and this data is going to work really well. So we're going to come back over here, and we're going to write that in a little bit more. The histogram indicates that the data is normally distributed. Okay. So yeah. Moving on, the null hypothesis, alternative hypothesis, so on and so forth. And I'm going to do this. Okay. So the null hypothesis. In order to determine the null hypothesis, remember all that we're actually comparing, all that we're actually evaluating is the mean difference. And the way that you write mean difference is mu sub d. So I'm going to actually take this and I'm going to click Format, Subscript, mu sub d. And that means the mean, the population mean of the difference scores is equal to 0. So for the null hypothesis, we're saying there is going to be no difference between the paired scores from Atlanta and Houston. And when there is no difference, the null hypothesis, when there is no difference, the difference between the two of them is 0. The alternative hypothesis is there is a difference between Atlanta and Houston, and so the mu sub d once again I'm going to do subscript, mu sub d does not equal 0. In other words, it's going to be on the left tail or the right tail. Houston is going to have the higher paired value, or Atlanta is going to have the higher value. But it's going to be one of the two, which is the alternative hypothesis that there is a difference. Okay, and so the next thing that we're going to do, I'm actually, well, I'm going to leave that there, but I want to show you guys how to calculate this test critical value, okay? So you can go to the t-chart to get the test critical value. Or you can use this fun little t.inverse.2t formula. So I'm going to do equals t dot inverse dot 2t, and I'm going to put the probability. What's the probability that we're going to use? Remember, we've got an alpha of 0.05. So because we've got an alpha of 0.05, let's see here, should we put 0.95? And then the degrees of freedom is going to be 83. Let's see if that works. So that doesn't work. And the reason why that doesn't work is because 0.95, that is one tail of the probability, or the center probability, but the probability that we're looking for is actually the probability of committing type 1 error. So the probability of committing type 1 error is 0.05. And you'll notice it gives us this wonderful 1.98896, which is even more accurate than the plus or minus 1.989. So I'm going to Control C, Control V, just paste the values, and then I'm going to copy, and the critical value is actually, you guys ready? Plus or minus 1.9889959 dot 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 dot. So this formula makes it so that you don't even have to go to the t table anymore. You've got that formula right there and you're good to go. So just make sure that you use the probability of committing type 1 error. And there's more information on all of these formulas. If you come down here to Excel formulas, you can find all of the formulas that I mention in here, and it tells you, hey, this is what you should be doing with them. Okay, so going back to paired, we're going to do the reject decision rule. Okay, so the reject decision rule is going to say we are going to reject the null hypothesis if t-calc is less than negative 1.989. So I'm just going to keep it rounded, or if t-calc is greater than 1.989. And if you look over here on the right hand side, I do explain things a little bit more, and I want you guys to explain things just a little bit more too. Like for instance, the null hypothesis, I have it written in symbols here, but I have it written as the average difference score is equal to 0. The average difference score is not equal to 0. The two-tailed test, 83 degrees of freedom, 0.05 alpha, use the t-table, or in this case, use the t.n.2t formula, or use the t-table to find the critical value of plus or minus 9 or 1.986. Sorry, one more thing that I need to mention to you is when I did the 2t, you notice that it didn't give me a plus or minus sign. You have to put in the plus or minus sign. So if it's a two-tail, and you use this formula, you still have to do the plus or minus sign. Okay. So we have the reject decision rule, and there's a little bit more information there, which is pretty much the same thing. And then the fail to reject, we're going to fail reject the null hypothesis if t-calc is between negative 1.989 or 1.989. Okay, and so then the t-calc value. In order to get the t-calc value, probably the hardest thing, we've got to come over here and we are going to run the test. By the hardest thing, I was being semi-sarcastic, but we're going to run the test and we're going to do data. And I'm going to come right here to data analysis, and I'm going to click on t-test paired two samples for means, and I'm going to highlight the variable 1 range, and then I'm going to highlight the variable 2 range. Okay, and they're right next to each other. And we are going to hypothesize that the mean difference is going to be 0 with an alpha of 0.05. And then for the output range, we're going to come down here and we're going to put the t-test right here and press OK. So now we have the t-test with the paired two samples for the means. So we've got the mean of each one of these, the variance, the number of observations. We also have the Pearson's correlation. In other words, they're very similar to each other. Degrees of freedom, and then we also have the t-test. And then the other cool thing is we've got the probability for a one-tail or the probability for a two-tail. So we have the t-statistic, which the t-statistic is going to be the same whether or not you have a one-tail or a two-tail. So I'm going to copy this, Control-C, and I'm going to come over here. And I'm going to put in right there. There we go. And what's the p-value? Okay. What is the probability of this occurring, assuming that the null hypothesis is true? Now, there are two p-values here, okay? Which p-value are you going to use? Are you going to use the one-tail, or are you going to use the two-tail? So it says two-tail right there, so make sure that you grab the one that says two-tail, because we already determined that we're running a two-tail test, okay? Two-tail test, and so we're going to come down here, and we're going to say, what is the p-value? There we go. And I want to point one more thing out for you. We've got the t-critical for a two-tail test. You notice it says 1.98895 ... And you come right up here, and it's the same thing. So we already calculated it, and then data analysis tool also calculated it, and it's the exact same thing for both, which is great. It's a nice little way to, make sure that you know what's going on. So we've got the test calculated value, and we write over here that it's determined from the data analysis Excel tool. The calculated value of the difference score is 2.09 standard deviations below 0. Okay, so we're just saying, hey, this is what it is. Then for the p-value, just tell me what the p-value is. Assuming that the null hypothesis is true, the probability of this occurring randomly is 0.03826. The truth is, I have all these wonderful descriptions over here. I am perfectly okay with you taking my descriptions and modifying them for your situation. Just make sure that you do modify them. I will check. I have this fun little tool that actually just goes through and checks all your answers. So the results are statistically significant, and the way that we know that the results are statistically significant is the p-value of, and notice for statistical significance, we're using p-value. So the p-value of 0.03826 is less than the alpha of 0.05. The results are statistically significant. Okay. And then to make a hypothesis decision, we're using the t t-calc value. So as the t-calc of negative 2.09 is more extreme than the t-crit value, or is beyond the t-crit value of negative 1.989, the null hypothesis is rejected. So we say what we did here, and we explain it over here. And then over here, what is the mean of the difference score? What is the average of the difference between the two? On average, Atlanta salaries are $934.60 less than Houston salaries when comparing the same occupation salaries with each other. Okay. And so once again, put the value right here, explain what that value means over here. Put the value right here, explain what the values mean over here. So how do we get this right here? The sample mean plus or minus a standard deviation. You literally have right here, you've got the sample means, and you've got the standard deviations. And you've got the difference score mean, you've got the standard deviation. And then you also have the difference score means, and then you've got the confidence levels right down here, the 95% confidence levels. This right here, these are the margin of error at a 95% CI. Okay, that's what these are. These are all margin of errors at 95% CI, which you can calculate them by hand. There's also this fun little formula right here where you can calculate those. But all of these, you should know how to do these inside and out. You take the standard deviation plus you take the mean plus or minus the standard deviation for each sample, or you take the mean plus or minus the standard deviation for the difference score, and explain to me that about 68% of these values are going to fall within this range. And then last but not 95% confident that the actual average of the difference score is between negative 1,822 and negative 47.11. Okay, last but not least, we've got the effect size, and then we're going to explain what we did. So what is the effect size? Is what you caught worth keeping? And in order to determine the effect size, we're going to come over here, and this is probably the easiest effect size that calculation that we're going to do. So we're going to put the mean right here. So let's put the mean of the difference scores right there. And then we're going to put the standard deviation of the difference scores right there. Okay. And so now we're going to do equals ABS, okay, of the mean divided by the standard deviation, and it's going to give us 0.22853. Okay, so you come right over here, 0.22853. This is a small effect size, and the reason why it's a small effect size is purely because of the massive standard deviation. If the standard deviation was smaller, watch this. I'm going to change the standard deviation to, I don't know, 400. That changes everything. That's huge. Okay, so if we had a much smaller standard deviation, even 1,000. If we had a standard deviation of $1,000, we would have much more precision, but we don't. So we've got we've got 0.22853. So we're gonna copy this, Control C, come down here, paste just the values, and we're going to come over here and say this is a small effect size, indicating that this is only noticeable with large sample size. It would not be easily observable. Okay. Now we're going to move on to writing a discussion results of this information. Well, I have just went ahead and typed all this up. That way you didn't have to watch me type it all up. What I actually did is I went into independent and I just copied this and I put it in here and I pasted it because they are very similar, and then I just modified it. And once again, you can do that as well. You can literally copy this, paste it into yours and modify it, so that way you can have a template for what to include. Can you tell I really want you to do well on this? It's set up for you to succeed. This is what we did. Look over on the left-hand side, and I'm going to hide this so that way we can see everything. Okay, so what was run? Okay, let's come over here. What was run? A paired samples t-test was run. Okay, comparing what? Comparing the differences of the average salaries in Houston to the average salaries in Atlanta paired on occupation type. Okay, so comparing the difference, there we go. What was compared? What was the result? The average difference between the salaries in Atlanta compared to Houston is negative $934.60. Notice I have Atlanta first, Houston second, with Houston having the higher salaries on average. What is the p-value? The probability of this occurring, assuming there is no difference between Atlanta and Houston, is about 4%. And then next, what are the possible factors that influence this? I'll get into that in a little bit, but I wrote right here, there were outliers both with Atlanta having higher salaries for 3 occupations and Houston having higher salaries for 2 occupations. This result is ironic, as Houston has the higher salaries on average. Next, uh, write about the confidence intervals and the standard deviations, whatever is appropriate. And I tend to write about confidence intervals over and over again just because I feel like that's actually one of the better metrics for practical significance. So we are 95% confident that the actual average difference of salaries between Atlanta and Houston based on occupation is between negative $1,822.10 and negative $47.11. Okay, and then as this range is below zero, okay, this range right here is below zero. This indicates that Atlanta salaries based on occupation compared to Houston are below Houston salaries. So because this is less than zero, because this range right here, this is the range and it is being compared to zero. If it's less than zero, then it is significantly noticeable, and it is going to be less. Atlanta is going to be less than Houston. If this range is greater than zero, where zero is not included in the range, then Houston salaries are going to be lower and Atlanta salaries are going to be higher, or the difference between the two of them would be that way. So as these two confidence intervals do not overlap, this is still left over, so let's get rid of that. Whoops. So this is talking about the effect size here. Okay, however, the results are not very noticeable with this outcome, and a large sample size is needed in order to see the difference. There's little practical significance and not much reason or logic contributing to why the two of these cities have differences in salaries based on occupation. I want to do something really quick. So basically what I just said here is there's a difference, but it's a small difference. We can barely even tell that there's a difference because there's so many that are above, so many that are below, and I'm going to run an independent samples t-test to show you all that if you run an independent samples t-test, you're not even going to get a significant difference. So I'm going to do data analysis, and I'm going to run an independent samples t-test assuming equal variances. And so I've got right here Atlanta, and then I've got variable 2 range Houston. Okay, 0 with an alpha of 0.05 with an output range. Let's put the output range right here. And press OK. So I just ran a t-test, and let's see what happens here. Where is that t-test? I don't know where it went. That's odd. Let's run that again. Okay, so I'm going to run a t-test, and I'm going to click on data analysis, t-test for 2 samples assuming equal variances, because I know that they're most likely the equal variances. So I've got Atlanta compared to Houston. Okay, so Atlanta compared to Houston, make sure that those line up. Okay, and then hypothesize mean difference of 0 with an alpha of 0.05. And then I'm going to have an output range. Let's get rid of that. Let's have an output range right here. and then press OK. And so I've got this output right here, and you will notice we've got the means, we've got the variance observation, and then we've got the t statistic, and then the critical value, so on and so forth. And what is the probability of occurrence? Comparing the two of these, let's look at this. I'm going to zoom in even further. Okay, these two are almost identical. Okay, if we didn't run a paired samples t-test, these would be almost identical. Okay, I'm going to do one more thing. I'm going to pause this. Okay, so what I did here is I made a pivot table, and then I made a frequency distribution, and after I made the frequency distribution, I made the frequency polygon. And if you look at this frequency polygon, these two distributions look almost identical. And I told you earlier, you see this probability right here. You've got close to a 40% probability of just randomly getting this just by chance. Or for a two-tailed, you have an 80%, which we ran a two-tailed, you have an 80% just by chance getting this if you run an independent samples with equal variances. And so it's really important. This data set right here demonstrates the power of pairing up samples. When you have a way to pair up samples, what this says with us doing this is that if you go to Atlanta, there's a lot of occupations that are in Atlanta that you're going to have a lot higher salary in Atlanta compared to Houston. And same thing, vice versa with Houston, you're going to have a lot of salaries in Houston that are going to be higher than Atlanta based on occupation. So it'd be really interesting to see what occupations are higher in Atlanta as compared to Houston, and which ones are higher in Houston compared to Atlanta. And so this is just a really, really great data set to demonstrate the power of a paired samples hypothesis test over an independent samples hypothesis test, and why, if you can pair up data, you definitely should pair up data. Now, you don't have to do this part. I just did all this part to show you the big difference between an independent samples and a paired samples, and I really hope that that was beneficial for you. Thank you so much, and hope that this was beneficial, and hope that this is all going really well for you.